calculate electrical demand in kilowatts from amps and volts, use the following formula. Electric demand in kilowatts equals amps multiplied by volts multiplied by the square root of 3 divided by 1000. The square root of 3 is approximately 1.732. In the provided example, we have 1200 amps and 480 volts. Plug in these values into the formula. We get electric demand in kilowatts equals 1200 amps multiplied by 480 volts multiplied by 1.732 divided by 1000. This equals 1200 multiplied by 480 multiplied by 1.732, which results in 997,660.8. Dividing this number by 1000 gives us 997.66 kilowatts. Therefore, the electric demand for the given values of 1200 amps and 480 volts is 997.66 kilowatts. Let's break down the components of this calculation further. Firstly, the amperage represents the electrical current flowing through the circuit. In this case, it's 1200 amps. Secondly, the voltage represents the electrical potential difference or pressure that drives the current. Here, it's 480 volts. Thirdly, the square root of 3, approximately 1.732, is a factor used in three-phase power systems. Three-phase power is a common method of electrical power transmission that uses three alternating currents to deliver power more efficiently than single-phase power. The factor of the square root of 3 accounts for the relationship between the line-to-line voltage and the phase voltage in a balanced three-phase system. Finally, dividing by 1000 converts the result from volt-amps, which would otherwise be the unit, to kilowatts, as 1 kilowatt is equal to 1000 watts. Therefore, the formula accounts for the three-phase nature of the power system and converts the result into the desired unit of kilowatts. Now, let's consider why this calculation is important. Understanding electrical demand is crucial for several reasons. Firstly, it helps in determining the appropriate size of electrical equipment, such as transformers, generators, and wiring. If the electrical demand is underestimated, the equipment may be undersized, leading to overloading, overheating, and potential equipment failure. Conversely, if the electrical demand is overestimated, the equipment may be oversized, resulting in unnecessary costs and reduced efficiency. Secondly, knowing the electrical demand is essential for energy management and cost control. By understanding how much power is being consumed, it is possible to identify areas where energy can be saved and costs can be reduced. This can involve implementing energy-efficient technologies, optimizing equipment usage, and adjusting operational schedules. Thirdly, electrical demand information is vital for utility companies in planning and managing their power grids. Utility companies need to know the electrical demand of their customers to ensure that they can provide a reliable and adequate supply of power. This involves forecasting future demand, planning infrastructure upgrades, and managing peak demand periods. Let's elaborate on the three-phase power system aspect. In a three-phase system, 3 alternating currents are supplied, each with the same frequency and voltage, but with a phase difference of 120 electrical degrees between them. This arrangement provides a more constant and efficient power delivery compared to a single-phase system. The square root of 3 factor in the electrical demand calculation arises from the relationship between the line-to-line voltage and the phase voltage in a balanced three-phase system. The line-to-line voltage is the voltage measured between any two of the 3 phases, while the phase voltage is the voltage measured between one phase and the neutral point. In a Y-connected system, the line-to-line voltage is equal to the square root of 3 times the phase voltage. In a delta-connected system, the line-to-line voltage is equal to the phase voltage, but the line current is equal to the square root of 3 times the phase current. The electrical demand formula we discussed assumes a balanced three-phase system, meaning that the load is evenly distributed across the 3 phases. In an unbalanced system, where the load is not evenly distributed, the calculation becomes more complex and requires considering the individual phase currents and voltages. Also, it is very important to use properly rated equipment. For example, the conductors must be sized appropriately based on ampacity to handle the 1200 amps in the example, There are many NEC tables that help with conductor sizing based on conditions of use. For example, NEC Table 310.16 provides ampacity ratings for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and installed in raceways. Also, make sure to use appropriately sized overcurrent protection, so that if there is a fault the circuit will safely open. Overcurrent protection can include fuses and circuit breakers. The size of the overcurrent protection should coordinate with the conductors. For example, the overcurrent protection should not exceed the ampacity of the conductors. There are specific NEC tables that describe how to size overcurrent protection. For example, NEC section 240.4b describes the next higher overcurrent protective device rating after the conductor ampacity has been calculated. All of these calculations are important to ensure a safe installation. The 997.66 kW is the electric demand. This figure does not represent the electrical consumption or the amount of energy used over a period of time. Consumption would be represented by kilowatt-hours or kWh. Electrical demand is like the instantaneous power being drawn at one moment, and it is used to size the electrical system. Electrical consumption is the amount of energy used over a period of time. One can think of a water analogy. Electric demand is like the diameter of the pipe, and electric consumption is like the amount of water that flowed through the pipe over a period of time. Also, electric demand is not something that is fixed. It varies over time as equipment is turned on and off. The electric demand calculation shown is for a specific point in time, based on the instantaneous amps and volts. If the amps and volts change, the electric demand will also change. Also, the electric demand that was calculated might not be the maximum electric demand. The maximum electric demand would be found during the time when the amperage is at its highest. The electric demand that was calculated is just a snapshot in time. There are devices called power quality meters that can record electrical parameters such as amps, volts, power factor, and kilowatts over a period of time. These meters can be very helpful in determining the electric demand and consumption over time. The utility company might also use these devices. Using a power quality meter would give a better idea of what the electrical demand is over time, instead of using a single calculation. The power quality meter would show the maximum electric demand and what time of day it occurred. Utilities often charge more money during times of peak demand, so these meters can help with energy management. In summary, the formula for calculating electrical demand in kilowatts is electric demand in kilowatts equals amps multiplied by volts multiplied by the square root of 3 divided by 1000. This calculation is correct for a balanced three-phase system. It is important to understand electrical demand for equipment sizing, energy management, and utility planning. Power quality meters can be used to record electrical parameters over time, which can provide a more accurate picture of electric demand and consumption. Always make sure to properly size the conductors and overcurrent protection to ensure safe installation. The calculated electric demand is just a snapshot in time, and it might not be the maximum electric demand. The maximum electric demand would be found during the time when the amperage is at its highest. Finally, the calculated electric demand is not the same as electrical consumption. Electrical consumption is the amount of energy used over a period of time, and it is measured in kilowatt-hours.